Welcome everyone to our third and final installment where we have been talking about Newton's Laws 1. My name is Vincent Weiss. I'm the Manager of Product and Training Development at See the Change USA. And today we are going to talk about forces and interactions. If you missed part 1 and 2 of this series, you can access those archived webinars in both the physics lab and our See the Change USA Edmodo group under Newton's Laws 1 inside either the folders area on the Edmodo group or the teacher content training area on the physics lab. So just a few items before we get started. First, for this webinar, there will be no audio or video. You will not need it. So if you have turned on your video, you can turn that off right now. This means we are going to use the chat box feature to communicate. To get to that chat box, put your cursor at the top of the screen, go to the far right where you see the ellipse, click on the ellipse, and then you'll see a chat item. Click on that chat and the chat box will come up. So the session will be recorded just like all the others, and you will be able to access these recordings afterwards, and we'll talk about where you can find those recordings at the very end. And also the PowerPoint used for this session will also be made available. So the purpose of today is first and foremost to build your confidence in physics. So you are all great science teachers, but we will not stop or rest until you become a world-class middle school physics teacher. This is what we want you to be. We want you to be the best of the best, the most knowledgeable of the most knowledgeable middle school physics teachers in the entire country and in the entire world. And until we reach that, we'll constantly be feeding you more and more physics. And also, this is to help you bring high-level physics content to the middle school mind. So a lot of the concepts that we talk about is very high level, but I don't think it's high level because it's difficult. It's high level because it's new, really. That's probably the main reason why it's high level. So throughout today's session, we are going to throw in little hints, tips, and tricks to help you bring some of this content and make it relative and make it accessible for middle school students so that they can grasp both these topics. And who is this for? It's for teachers looking to take their students to a deeper level of understanding. This is not your mother's middle school physics. This is some serious stuff that we're talking about, and we want every one of these students to understand physics on a level so that when they get to high school, their high school teachers can say, man, I have nothing else to teach them. They know these concepts. Or they can say, great, these students know these concepts, and now I could just tack on the math, and it's not something so difficult. And we want This is also for teachers who do not have an extensive background in physics but would like to master the concepts. So if you are sitting here and say, I don't know any physics and I never took any physics in high school or in college, and it's really a topic that I'm scared of or I struggle with, well, you're in the right place because I am going to do my best to break these concepts down so much that you can look at it and grab it and say, you know what, I can take this and run with it. And this is also for teachers looking for alternate ways to explain concepts to your students. There's always many ways to explain the same concept, and hopefully there's a few concepts and explanations in here that you can run with. Okay, so what we will cover the content found in lessons 1.3.12 through 1.3.16. So these are the last few lessons in the unit 1.3 Newton's Laws 1. So we will look at important forces that affect the motion of all things on the earth, and we will look at the fundamental forces of nature that make up every interaction in creation. And finally, at the end, we're going to have a question and answer session about the content found in, not these lessons, but the very last lessons in the unit. All right, so without any further ado, let us get started. So, Newton's Laws 1, forces and interactions. So all forces can be broken into two different types. There are what we call contact forces and non-contact forces. So contact forces would be things where two things are touching. So if you push an object, that's a contact force. Non-contact forces happen when two things are able to interact with each other without touching. So Some of the most important contact forces, starting with the most common, is just direct pushing or pulling. So here we went over this example last time, these boys pushing and pulling this wagon. So everywhere there's either a push or a pull, there's a force. So we can take these forces, we can line them head to tail, and then we can find the net force. And it's that force that's going to tell us how exactly this wagon will move. After that, there's a very important force that it's easy for us to forget, but we need to always keep it at the forefront of our mind. It's this normal force. Now, normal, not making it sound like it's just a really normal force. Hey, that's normal. Well, normal is a mathematic term that stands for perpendicular. So when we hear the normal force, it refers to a perpendicular force, and it's a force that's perpendicular to a surface. So that's really what the normal force is, a force that just comes from a surface that's perpendicular to a surface. So important thing about the normal force is that it keeps objects from falling through the ground. This is super important because remember, we always get gravity pulling things down towards the ground. There's got to be a force that counteracts it so things stop moving. And as this book is not moving, even though it has the force of gravity, there must be another force counteracting the force of gravity. And we call that force the normal force, and it's perpendicular to the ground. So another really important force is the force of friction. So oftentimes in physics, we are looking at idealized situations, and all the time we use this term neglecting the force of friction, or assuming there is no friction, or assuming there's no air resistance, which is another type of friction, and on it goes. We're going to look at this problem. And the reason we do that is a lot of times when we're teaching about physics concepts, it's easy to get bogged down in this concept of friction because it actually makes problems really difficult. But it's really important because things don't happen in idealized situations. Every time something moves, it's probably going against some force of friction. And just to talk about it is it actually it's important to constantly keep in mind that real things operate in a world where there's lots and lots of friction. And I would just encourage you that even though in Newton's Laws 1, we don't dig deep into friction, that will come in Newton's Laws 2, but I'm going to introduce it here. But it's really important to constantly remind your students that they're dealing with idealized situations. I had a physics professor that had a very unique way to remind us that what we were dealing with was an idealized situation. And he did it in the form of a joke. So the joke goes like this. There was a farmer who had something wrong with his chicken. So his idea was go to the town physicist and say, you know what, this is a big problem. He can probably figure it out. So he takes his chicken to the town physicist and he looks over the chicken and he says, you know what, I think I can solve this problem. But let's first assume a spherical chicken. And that's the joke. And the joke is physicists are always making crazy assumptions to idealize the situation. So whenever we came to a situation where there was no friction or something was assumed, he would always make that statement, let's assume a spherical chicken and yada, yada, yada. There's no friction, there's no air resistance, there's none of this, and we're going to make this problem more idealized. So just talking about friction, always remembering friction is involved. So let's talk a little bit about what it is and how it affects an object's motion. So imagine you have this guy pushing this chest, and now let's imagine something that we usually don't imagine, but there is friction. So as he slides this chest across the ground, friction is playing a role. So he applies a force in one direction, and the force of friction is like a force, someone pushing in the opposite direction. And that's how friction always works. It always moves against the applied force or against the motion. So if instead he decided he wanted to pull the chest in the opposite direction, well, the force of friction would flip and it would start resisting any changes in motion. So when we look at friction, it's good to ask the question, what factors affect the force of friction? And so here we have this green little box across this surface, and it would appear as though both of these surfaces may be perfectly smooth. But it's important to remember with real things, nothing is perfectly smooth. That things are made of, even once we get in looking at an object, if you were to take the smoothest piece of paper and look at it under a microscope, and crank up the magnitude of that microscope, then all of a sudden that smooth piece of paper doesn't look so smooth anymore. So if we were to able to zoom in and see what was happening, we would see a very rigid surface. And you can imagine there would be a lot of resistance if these two objects started scraping against each other. And this rigid surface is what causes the force of friction. So if we want to know what are the factors that affect friction, obviously it's the texture of the surface the object is rubbing against, but it's also the texture of the object that's rubbing against the surface. And you can also imagine, well, what if we take this box and stretch it out so more of that surface is rubbing against the orange surface? So surface area is also a factor that affects the amount of friction. One beautiful example of surface area, if you take two books and start interweaving their pages together so that you have one page from one book and then you overlay another page and then overlay those pages together, then the surface area between all of those pages becomes enormous and the force of friction becomes huge, such that after you've interwoven all of those pages, you'll not be able to pull those books apart because the force of friction is so great. And there's also one more thing. Imagine if this box became really, really heavy. Well, it's going to scrape across that surface and there's going to be more resistance. So the weight of this green box also affects how much friction is going to be involved as you try to slide these surfaces together. So this is really a topic that the students will dive into for Newton's Laws 2. So if you're actually teaching Newton's Laws 2, one great inquiry lab would be to see if the students can play around with a few surfaces, with a few objects, discuss friction, and see if they can identify all the factors that affect the force of friction. But so I guess, yeah, from here, if we have these four things that affect friction, what physicists will say is that the things on the left, the texture of the surface, texture of the object, and the surface area of the object, we will wrap all of those ideas in one single variable, and we'll call that variable this Greek letter mu. So mu is a number that represents all of those three things. And the weight of the object, we will find out when we talk about force of gravity, is equal to the mass of the green object times this number g, which is 9.8 meters per second squared. So these are the two things that affect the force of friction. And if you multiply them together, you get exactly that. So if we come back to this guy pushing this chest, and we're interested, what is the net force acting on this chest? We can simply add these vectors together. We can take the applied force minus the force of friction. Notice it's a minus. It always gets a minus because it always resists the applied force, so it takes away from it. But as we saw, the force of friction is equal to this mu mg, and this would be the net force acting on this chest. So one fun thing that I like to ask students about, just to get their minds and imagination land, I got this hypothetical problem, because it seems as though friction, the more friction an object has, the harder it is to move. If we think of pushing something through on a really rough surface, becomes more difficult to move. But what if there was some mysterious object that if it was sitting on a surface with no friction, it would just stay there? But notice over on the right, imagine I had this special box that if I can turn this knob to increase the friction of this surface and just increase the roughness, what type of object would it have to be such that if I increase the friction, the object starts to move? This is a fun little mind teaser, so if you're on these topics and you just want to give the students some break um, with all the things that they're learning, you want to give them something that, brain teaser, this is an excellent brain teaser. What could this mysterious object be? Well, as it turns out, it is the spinning wheel. Wheels are special in that they actually work better the more friction there is. And the strange thing is that no energy is lost on the edge of the wheel if it's sliding across a surface that has plenty of friction. And this is what makes wheels so efficient when dealing with friction, is that they pretty much eliminate the force of friction. The only force of friction that's lost comes between the wheel spinning on its bearing, and that's where friction is lost with the spinning wheel. So whenever you're dealing with heavy objects that you need to move, it's always easier to put it on a dolly with spinning wheels because it dramatically decreases the force of friction. So for a wheel has a very small mu. And this is what makes wheels so helpful, in that it pretty much eliminates the force of friction. So that's friction. Another very important force is the elastic force. Now let's take a look at the elastic force. Here we have a spring. And if we were to place a mass on that spring, it will stretch a certain distance d. And if we just take a look at the forces on this spring, we see we have the weight pulling it down. But if it's not moving, there's another force that is counteracting that weight, and we call that force the elastic force. And if we just put another mass on it, it stretches even more, but now it has double the weight stretching the spring, so the elastic force doubles. And this is the important concept about springs, that the further you stretch it, the greater the force, greater the elastic force. So springs get harder to stretch the longer you stretch them, but some springs are meant to compress, and the same is true. Springs get harder to compress the shorter you compress them. The reason this force is important is because so many things can be approximated as springs. So here is an example of some Stretch Armstrong guy and these two kids pulling him apart. The further they pull him apart, the harder it will be to pull him apart. And we can approximate Stretch Armstrong as a spring, with an elastic force trying to pull him back together. The bow and arrow can also be approximated as a spring. As you pull that bow back, the harder it becomes to pull back, where you have these equal and opposite forces canceling each other out. So we can approximate this as a spring. Also the ground. The ground doesn't seem like a spring, but if you imagine the ground as a bunch of really, really stiff springs, we can actually approximate the normal force of the ground as a very stiff spring. We can approximate balls also as springs that bounce up and down. And this happens to be a basketball, but imagine a golf ball. A golf ball doesn't seem like a spring, but we can imagine it as a very, very stiff spring. And actually, when they're designing new and better golf balls, what they do is that they take these golf balls and they use high-speed cameras, and they can measure how much that golf ball compresses when it's hit with the head of a golf club, and they can calculate exactly how much energy is lost to compress that golf ball, and they use the exact same equations that they would use for a spring. So it's a force that comes up everywhere in physics. So that is the elastic force. And what is important to note is it's common for students to think that these forces exist in isolation. But as it turns out, these forces pop up maybe multiple times in one little scenario. I'll give you an example. Imagine you take a rubber band and you put it on your thumb and you stretch it back and then you fling it forward. Well, there's multiple of these going on at one time. There's the direct pushing or pulling, so there's the force of pulling that rubber band back. There's the normal force, which comes from your thumb as it pushes against that rubber band. And then when you release it, it's flying through the air, so there's the friction of air slowing it down. And then there's the elastic force that comes from the stretch of the rubber band. So that one example, you can find all of these forces. So one of the important things to take away from just these contact forces is to challenge your students not to only think about the one net or one applied force, but to look at the problem at hand and try to analyze all the single possible contact forces that could be affecting that object's motion. And then when they're exposed to more mathematics and they're exposed to ways that they can actually add these vectors together, then it will be like simple nature to identify the forces, and then it really just becomes a math problem. And the mathematics can get a little hectic, but it's good for them to know these fundamental ideas before they're exposed to any of the math concepts. So that's non-contact force. Now we're going to talk about, non-contact forces. So these are forces that exist without things touching each other. So the most famous of all of these is the force of gravity. So let's take a look at the force of gravity. So you imagine you have these two clumps of mass. If they have mass, there is a gravitational interaction between these two clumps of matter. So this object is attracted to him and he is attracted to him, and they impose equal and opposite forces onto each other. This is a consequence of Newton's third law of motion, that for every action there is an equal and opposite reaction, or what we learned last time, that actions and reactions are really forces. For every force there is an equal and opposite force, and this is another way of saying that. And that causes these two clumps of mass to come together. So now let's label these two clumps and let's ask the question, what is the force acting on this mass from this mass? So what is the gravitational force pulling M1 towards M2? Well, we know the force of gravity is related somehow to the mass of this first clump and the mass of this second clump and the distance separating these two clumps of mass. And this distance actually is the distance from a very special point called the center of mass. So they are separated, and what we mean is they're attracted to their center of mass. So here is what looks like a math equation. And the reason physicists make these equations because it's much easier to write an equation than to explain things in words. And it's important to remember that mathematics is a language. And at this point, we can start talking about what these languages say, because this says something. It actually says quite a bit, but in one simple equation. So let me break this equation down and talk about what it actually means. Starting with the first part with these two m's on top of this d squared. So what do these two m's together mean? Well, this is m1 times m2. Basically, this says that as the masses get bigger, the gravitational force gets stronger. The important thing to note is that it's dependent on both mass. So mass of M1 and the mass of M2. It's not as if the first mass just creates this gravitational field independent of anything else. Gravitation is an interaction between two or more things. So with this concept, we can easily see why the Earth has such a large gravitational effect, because any mass around the Earth, the gravitational interaction of, let's say, your body, gets multiplied with the mass of the whole Earth. So this makes a huge effect, and this is why we all feel the effects of gravity. So that's the top part, but what about this bottom part, d squared? So this is called an inverse squared relationship. Inverse because it's in the denominator, and squared because it's squared. And as it turns out, nature really likes these inverse squared relationships. This is true for gravity, and as we should see, it's also true for the electric force. So what does an inverse squared relationship mean? So imagine you have these two masses, M1 and M2, and they're separated by this distance right here. And this curve represents the force acting on these masses based on where they're located. So if we move M2 towards M1, notice the force gets really, really strong. So one question your students may ask if they see this, they say, if this is true, if the force increases the closer two masses get, then why is it that I can pick up something and it's not stuck to me forever, but I can take my hand away without it sticking to me? And if they ask that question, first thing I want you to do is commend them, because if they're asking that question, then you can tell immediately that they understand what this graph is saying, because it says that as two things get closer together, the force between them increases. So if you're dealing with this question, we need a way of answering it. And here's the answer. This is assuming that the only thing in the universe is mass. But as it turns out, there's other things in the universe, like electric charge. And whenever two things get close enough together, then there is some electrical interactions that take place that actively push or resist the gravitational force. For example, if you just push your finger down onto the table, you will notice that your finger is not permanently stuck to the table, but the table seems to be pushing back on you. That push actually comes from the electrical interactions between the electrons in your finger and the electrons on the table. So electrical interactions are the reason things don't clump together. If there were no electrical interactions, all the things in space would clump together in one big giant clump, and they would never leave each other. So this only happens when things are super massive. Black holes are incredibly massive that have such a strong gravitational effect that even the repulsive forces can't keep things from clumping together. So I showed this graph, but the graph is really not to scale. If it was really to scale, this curve would look a little more like an L. But it's just a way to demonstrate the electrical interaction takes place when they're closer together, but it takes place before the force gets really huge. As it turns out, the gravitational force is really weak compared to the other forces. And we only see it for very large bodies like planets and moons, but we don't really see it so much between everyday objects because the force is really just not that strong. But since we've brought up the Earth, so what about the force of gravity between objects and the Earth? This is an important question. So let's take this graph and let's superimpose the Earth onto this graph. So if we were to do this, here is the Earth. And this distance from here to here represents the distance between the center of the Earth and the surface of the Earth. So remember what I said before, objects are attracted to the center of mass of other objects. And if we were to just take this graph, then this line right here represents the surface of the Earth. And if we just come up here, the height of this curve right here, so this point right here, represents the gravitational force acting on an object close to the surface of the Earth. If this graph was a little, I would say this graph is a lot more to scale than the other one. So using this graph, it's easy to see that out here, which would be equivalent to the distance the International Space Station is from the surface of the Earth, just several miles up, and notice the change in the force of gravity between here and here. There's barely any change at all. So what does this mean? This is telling us that the force of gravity acting on objects at the surface of the Earth is actually quite close to the force of gravity acting on things on the International Space Station. And if the student asks, wait a minute, why do things seem weightless on the International Space Station or in space if there's so much gravity? And again, if they ask this question, you need to commend them because they understand the implications of what this graph is telling us. The reason astronauts are weightless in space when they're on the International Space Station is not because of the lack of gravity. This graph is telling us there's plenty of gravity. There's almost just as much gravity acting on them as acting on something on the surface, and that's absolutely true. So we will actually get to that reason in Newton's laws 2. So we're not going to answer that here, but we'll answer that in Newton's laws 2. So if you really want to know the answer to that question, then I would encourage you to watch this, watch the training for Newton's laws 2. But it's an excellent question, and if a student asks it, then it means they understand the implications of this graph. So if the International Space Station experiences very little effect, then how much more objects that are really close? So let's say you lift an object just 100 feet above the ground. Does its weight change? In fact, no. You take a 50-pound weight and lift it 100 feet up and then weigh it, it'll be 50 pounds. I mean, it'll be the exact same weight. So what this graph is telling us is that we can make a huge simplification to the force of gravity because the force doesn't actually change. So close to the surface, the force of gravity barely changes, and this is really, really helpful. So instead of having that big long equation where you have m1 times m2 divided by the distance squared, we can simplify it down to this equation. And what's so neat is that what this what this equation says is that force of gravity acting on any object close to the surface of the Earth is equal to its mass times g, which is the acceleration due to gravity, 9.8 meters per second squared. So everything about the mass of the Earth, the distance we are from the center of the Earth, and the gravitational constant, which we haven't talked about yet, is all summed up in this 9.8 meters per second squared. And the reason we can use this is because gravity barely changes from one height to another height. And this is called the force of gravity, but this is also the equation that tells us the weight of an object. So when we use that word weight, what we really mean is the force of gravity. So let us use this. So imagine you have a baseball and it's falling towards the ground, and we're interested to know what is the motion of this ball as it falls towards the earth. Well, we know it has the force of gravity acting on it, and that's equal to m times this gravitational acceleration, g. If we assume that there's no air resistance, then we can say that this is actually the net force acting on the ball, because it's the only force. So now using Newton's equation, A is equal to the net force divided by the mass. We know the net force is mg, and there's an m on the top and bottom, so those cancel out, and we're simply left with g. So we know that the ball will accelerate towards the ground at 9.8 meters per second squared. Few things. First and foremost, notice that I never specified what the mass of the baseball was. The masses cancel out. And this is extremely important, because what this tells us is that every object close to the surface of the earth will accelerate towards the ground at the exact same rate. And you can do a lot of fun with this in a classroom with your students. So one of the fun things to do is to grab two objects and ask the students in the class which object will fall to the ground which object will fall to the ground faster. And they'll try to judge which one looks heavier, because we all assume the more mass an object has, the faster it will fall to the ground. But what this is telling us is that the mass doesn't matter. You can drop a tank, you can drop a penny, you can drop a feather, and they'll all fall to the ground at the same time. So what's fun to do is to take maybe a really heavy object like a big book, and then a light object like one single piece of paper, and then ask them which object will fall to the ground faster. And they'll all say the piece of paper. But at that time, what I like to do is take the paper, crumple it up, and then drop both objects so that they hit the ground. And what they'll see is that they both hit the ground at the exact same moment. And then maybe say, oh, it's because you crumpled the paper, but that has no effect on the mass, because the misconception is that the heavier the object, the faster it's going to fall. And I would encourage you, after that, take two more objects and then drop them, take two more objects and drop them, and keep on asking which object is going to hit the ground first. And when they finally when they all say that that the objects will hit the ground at the same time, then you know you've just permanently put something in their minds. They will constantly remember that things fall at the same rate. Another very important part I want to make here is that an object will accelerate towards the ground at 9.8 meters per second squared. So one thing I like to ask students is, how fast will an object fall to the ground? And just about every student likes to say it will fall to the ground at 9.8 meters per second squared. And I said, that's not the right response. And they say, well, what do you mean that's not the right response? Everything falls at the same rate. And I said, how fast will the object fall to the ground? See, the right response to that question, there's two different right responses. Either, well, how long did it fall, or how far did it fall? Because 9.8 meters per second squared means that the object speeds up. So if I ask the question, how fast will it fall? Well, that depends on either how long it's been falling or how far it has been falling. It's all dependent on a few things. So 9.8 meters per second squared doesn't describe how fast something goes, but it describes how fast it speeds up. So these are two important remarks that I wanted to make. All right, another very common misconception about gravity. It's commonly believed that since the Earth is so big, it must pull on the moon with more force than the moon pulls on the Earth. After all, the Earth is huge. It's got to apply a really big force on the moon. And the moon is so small. How can it apply that big of a force? And this is coming from the assumption that the Earth, without the moon, would produce this gravity pull. But what's important to realize is that gravity is an interaction between two objects. And as it turns out, Whenever any two objects interact, according to Newton's third law, they apply equal and opposite forces to each other. This means the moon pulls on the Earth with the exact same force as the Earth pulls on the moon. It's not as if gravity were separate from one another, but it's because these two objects are interacting, because any force is an interaction, but they must share the same force. The moon wants to go to the Earth just as much as the Earth wants to go to the moon. But we end up seeing the moon move around because Newton's second law, the moon just isn't as massive. So it's the one that gets thrown around the Earth instead of the Earth being thrown around the moon. The more massive an object is, the less its acceleration. And the moon will accelerate a whole lot because it's not quite as massive as the Earth. So the effects of this force is different, but the force itself is the same. But now that the moon is not close to the surface of the Earth. So unfortunately, we cannot make the same assumptions that we made with objects close to the surface of the Earth, with saying that the force acting on the moon is equal to the mass of the moon times the rate of gravitational acceleration, g. Unfortunately, we cannot make that assumption because it's much farther from the surface. So we're left with this long, ugly equation. And notice there's a minus sign. Anytime we see these long equations with a minus sign, this means that this force is an attractive force. So m1 would be the mass of the Earth, m2 would be the mass of the moon, and d squared, or d, is the distance between the center of the Earth and the center of the moon. And this big G is a universal gravitational constant that accounts for how strong the gravitational force is. And since I said the gravitational force is small, you can imagine that this big G is quite small. The nice thing is that this equation is universal. It applies to the Earth and the Sun just as much. We just need to change these values and we can calculate the force between the Sun and the Earth. And it's all of this balance, this equation in action, that keeps our solar system in harmony. So it's kind of a neat thing. So that takes care of gravity. Now let's talk a little bit about the electric force. So here we come to this clump of mass again, and we said that mass is the reason there's gravity. So if we zoom in and look inside this clump of mass, we'll find tiny little particles, and we call these particles atoms. And if we look inside the atom, we will see that it's filled with more particles. And there are two particles that are important. The first is a particle called the proton, and the second is another particle called the electron. Now, both of these particles have mass, but since their mass is so tiny and since the force of gravity is so weak, we can neglect the effects of gravity on the atomic scale. We completely neglect it. Imagine it's not there at all because it's that weak. But they carry something else, which is extremely, extremely important, and that something else is called charge. This is how charge works. So a proton carries a positive charge, an electron carries a negative charge. Now, like charges, they repel one another, and opposite charges are attracted to one another. And the strength of the electric force increases as the charges get closer together. So here we have these two charges, and they are attracted to one another. And as they get closer, that force grows, and as they move apart, it shrinks. And the strength of the electric force increases when the charges are separated. So imagine we have these two chunks of charges, and because both contain an equal number of positive and negative charges, there's not a very strong force between these two clumps of charges. This is why we don't feel the electric force on just about everything we touch, because there's an equal number of positive and negative charges in just about everything we come in contact with. But if we start separating these charges, then this force increases and we get this net effect. So we see this if we were to take a balloon and rub it against either the hairs of your arm or the hairs on your head, and what you actually do is you start separating the electrons from your hairs, and they start sticking to the balloon. And as they separate, there is an electric force that you can actually feel. So your hairs lift up because they are now feeling this electrical effect. And believe it or not, it doesn't take that many charges before you start feeling this effect, because the gravity or the electrical force is really, really strong. So that pretty much sums up the electrical force. Now let's talk about the magnetic force. Now before I get into this, I remember the first time I was really exposed to this in my first physics class. This force really confused me. And it wasn't until many years later that I thought about why it was so confusing. And I realized it's because I thought the magnetic force was one thing based on my experiences, when it turns out it was something completely different. Because physics always happens to talk about very non-intuitive things. And what I'm going to try to do is tell you what the magnetic force is not, and from there I will tell you what the magnetic force is. Yes. So I will just say that the magnetic force is more than likely not what you think it is. So starting with this, here we have two magnets, and every magnet has a north and a south pole, and everyone knows that like poles repel each other and opposite poles attract one another. So with this concept, we can use these ideas and explain why the magnets flip and stick together. And these poles are attracted to one another, and like poles repel one another. But the question is, what role does the magnetic force play in bringing these magnets together? It would seem as though these forces cause the repulsion and the attraction. So here we're going to kind of talk about what it can possibly be. So every magnet, it has a north and a south pole. This is kind of like a bar that somehow has a bunch of positive charge on top and a bunch of negative charge on the bottom. And we can call this a positive pole and call this a negative pole. But these two things are, as it turns out, completely different. So one we call a magnetic dipole, di meaning two poles, north and a south pole, and the other we call an electric dipole. One famous example of an electric dipole is actually a water molecule. The way the hydrogen is attached to the oxygen makes one side of that molecule positively charged and the other side of that molecule negatively charged, which is why it is such a great solvent. But let's talk about why these things are so different. So the electric dipole, we can take and we can do something to separate the charges. This may not be easy, but it's possible. It's always possible to separate the charges in an electric dipole. But if we try to take the magnet and maybe break it in half to separate its poles, we end up with two smaller magnets with a north and a south pole. Maybe we just need to break them in half again, and we can break them in half again, and we end up again with a bunch of north and south pole magnets. And we can continue breaking them and breaking them smaller and smaller and smaller down to the very particles. And what we will notice is that it is impossible to separate the poles of any magnet. Because it's impossible, there's no single magnetic poles in nature. And this presents a lot of problems when we try to explain what the magnetic force is. So one could be thinking, well, perhaps there are magnetic charges. There's a north charge and there's a south charge, and they interact with each other in a very similar way, like a positive and a negative charge. And this explains why magnets come together. But the problem is this is not reality, because magnetic charges don't exist. And because we can't have magnetic charges, we're forced to conclude the magnetic force is not an attractive and repulsive force. This is why I had such a hard time understanding magnetism, because our experiences tell us that magnetic forces are repulsive and attractive forces among magnets, right? As it turns out, no. The magnetic force does one thing and one thing only. The magnetic force redirects moving charges. That's all it does. What do I mean by that? So imagine you have here a little electron and you send it flying through this magnet. Well, the magnetic force redirects that motion. That's all it does. That's all it can do, and that's all it will do. So if this is true, why the heck do magnets come together? So I'm going to offer an explanation for this. And as I offer this explanation, if you listen to it and say, you know what, still doesn't make sense, it's okay. Because this idea took some of the smartest men in all of physics to come up with. And if it doesn't make sense, it's all right, because really when I think about it, I don't know if it makes sense to me either, but it's what we're forced to conclude. So why do these things come together? First and foremost is both of these magnets produce a magnetic field. We will get into this much more deeply, on how they create a magnetic field if you take electricity and magnetism, but mostly it has to do with the motion of all the electrons inside these magnets. But in any case, they produce magnetic fields. So these fields interact with the moving charges inside the other magnet. So for most materials, if you bring a magnet to a piece of wood, it's not going to affect the wood because the electrons moving in that piece of wood are moving in very random directions. But this is not the case for another magnet. Inside a magnet, the electrons are moving in very uniform, very specific ways. Because they're moving in very specific ways, there is a much bigger net effect on how these electrons are moving, and this gives rise to a small electric force. And it is actually this electric force that causes like poles to repel and opposite poles to attract. So it's the electric force that causes these things to stick together, but it's the magnetic field or the magnetic force that allows that electric force to actually have an effect. And as I said before, if you're not satisfied with this explanation, it's okay. Yeah, it's okay because yeah, it's a difficult pill to swallow. But in any case, some of the smartest men in all of physics came together, and this was their conclusion. That it was their conclusion. But the reason we have to go with this crazy explanation is because we have not been able to identify single poles, magnetic poles in nature. We can't find a north charge and a south charge. In fact, if you or your students were able to find these charges, then we can do away with all this crazy explanation and say, well, there's just a repulsive and an attractive force between charges, magnetic charges. And in the process, you'll win yourself a Nobel Prize. But until you can find these things, we're forced with this crazy explanation for how magnets work. So that's the magnetic force. Now let's get into the strong force. So here, remember, we have the atom, and inside that atom are particles. Now we're going to focus in on this little clump right in the very middle. That little clump is called the nucleus, and inside the nucleus there are two special particles. First one is called the neutron, and the neutron has no charge at all. The second one is called the proton, and the proton carries a positive charge. Now, if we look at this nucleus, it has a diameter, a very, very small diameter of about 0.000000000000084 meters. Give you an idea how small this is. Think about one single piece of paper. Now take that paper in your mind and say, you know what, we want to make the world's thinnest book, and we want to make it so thin that it has the thickness of a single piece of paper. And we want to make that book 1,000 pages long. So you have a single thickness paper and divide it into 1,000 pages. Imagine how thin one of those pages is. But now let's say, you know what, we can make this even thinner. Take that page and divide it into another 1,000-page book and take one single one of those pages. Imagine how thin that page would have to be. But let's go a little further and take that super thin page and let's divide it into another 1,000-page book and take one of those pages. And let's say, you know what, this is not quite thin enough. Let's divide it into 12 pages. And then take one of those pages. The thickness of that single tiny super thin page would be the thickness of this tiny little nucleus. So remember, inside this nucleus are protons, and protons are positively charged and they repel each other. So when we look at something with particles that are so close together that repel each other, we need to be thinking, what is the force acting on these particles? And this is the graph that represents the force acting on the particles separated by a distance d. As we move these particles together, the force gets huge. And when I mean huge, I mean huge. Pulsar force between neighboring protons is huge. It is a force on the macroscopic level. Now, whenever you take a microscopic thing and apply a macroscopic force to it, it will move very fast. Very quick. So the question we have to ask ourselves is, why do these particles not fly apart? It's a good question. There must be another force that is holding them together that is stronger than the electric force that's trying to push them apart. We call this force the strong nuclear force. The strong force is just an abbreviation for it, but the strong force acts between protons and protons, protons and neutrons, and neutrons and neutrons. So there's a couple things we know about the strong force. The first is that it's much stronger than the electric force, actually 100 times stronger. And the second thing is that it has a very short range. It only operates on that very, very, very tiny scale. It's not like the electric and gravitational force, which can extend very far distances out into space. And there's a lot more interesting stuff. I'd like to talk about the strong force, but you'll have to wait until we start talking about nuclear physics, because as of right now, this is about as far as we're going to go. So that's the strong force. Now let's talk about this mysterious weak force. So looking at the weak force, imagine you have a neutron, one single particle that has no charge on it. If you wait about 10 to 12 minutes, all of a sudden that neutron kicks out an electron and it becomes a proton. So the question is, what crazy mysterious force would cause an electron to separate from a proton? Because remember, these two things are oppositely charged and they should be attracted to one another. Could it be the gravitational force? Well, it's not the gravitational force, because as far as we know about the gravitational force, it only causes things to come together. So it's always an attractive force. What about the electric force? Well, it can't be that either, because negative charges don't repel positive charges. What about the strong nuclear force? Well, it can't be that either, because as I said, the strong nuclear force only operates between protons and neutrons. So this was all we knew. So there must be some other force, and we call that force the weak nuclear force, because it happens in the nucleus of the atom. So here we have these four forces. And the only thing missing is the magnetic force. So if we tack on the magnetic force to the electric force because, as it turns out, these two forces are so intimately related that they are very similar forces. And Einstein's relativity showed that they are actually two sides of the same coin. So here we have these four forces, and together they make what we call the four forces of nature. And what's so interesting is that just about every force in nature can be explained with one of these four forces. And when I mean every force, I mean every force, even all of those contact forces I was talking in the beginning. Because as I mentioned before, imagine you push on an object. That's a repulsive force. So pushing on an object comes from one of these four fundamental forces. It's not the gravitational, and it's not the strong or weak. It actually is the electromagnetic force of the electrons in your fingers and the electrons on the object that you're pushing that cause that object to move back. Or imagine a piece of tape. If you put your finger on a piece of tape, it sticks to you. Why does it stick to you? Because there is an electrical interaction that causes the atoms on that piece of tape to stick to the atoms on your finger. So when I mean every force in nature, as far as we know, can be explained by one of these forces, I mean every force in nature, as far as we know. So that's all we have on forces and interactions. So right now I want to open it up to any questions you have about any content that we have just gone over. So open this up to questions. Okay, so it seems as though there's no questions. I'm going to bring up next time. So we're done with Newton's Laws 1. Next time we're going to start a teacher training on Energy 1, where we'll be talking about work in simple machines. That will be on January 14th, 2015, and we will meet at 4:30 Mountain Time. So you can gain access to this recording or PowerPoint on both the Physics Lab and also See the Change USA Edmodo group. Actually, correction, you can get access to the recording on both those places, but you can only get access to the PowerPoint on the See the Change USA Edmodo group. So I would highly, highly encourage you to get onto that group. To get onto that group, to actually gain access to the group, I want to take you to the Physics Lab. Put on new share, this guy. You can get there easily from the Physics Lab by clicking on resources and clicking on links. And then here's a link that takes you straight to the See the Change USA Edmodo group. There's a join request if you have not joined, so click join. And you may need to create an account, but it's a simple username and password, and you can get a free account. And then you'll have access to all the PowerPoints, to all the different things that we've been talking about in this series. And as always, for additional teacher content training and support, I want to direct you to the Physics Lab. Under Newton's Laws 1, there is a teacher content training tab. Click on that and you will find additional videos talking about different ideas found in Newton's Laws 1. You can also post discussions, post questions, post thoughts on the See the Change USA Edmodo group, an excellent place where you can not only access the expertise of us here at See the Change, but you can also access the expertise of other teachers. So a really, really great resource, and I would encourage you to go there. Or you can always email me at vincent.weiss@seethechangeusa.org, or email Laura, whom you all know, at laura.horvath@seethechangeusa.org, or give us a call at 1-888-843-0671. Okay, and if there are not, this is the same stuff. All right, so if there's not any other questions, we want to thank you so much, and very excited about getting into Energy One, and we will see you all on January 14th. So thank you so much, and we will see you all later.